Okay, so finally for this section, we're going to look at Helmholtz theorem. And what we're going to focus on here is curl-free and divergence-free fields. So if we first look at the first one, the curl-free field, what we can write is the curl of our vector f is equal to 0. And when we have this, okay, so it means that the curl of our vector f is 0 everywhere. What we can write this as is f is equal to the gradient of some scalar potential v. Okay, so let's look at this in a little bit more detail. So first of all, what I want to do is write up Stokes' theorem again. Okay, so we have the surface integral of some derivative. In this case, it's the curl of f. With dA, again, it's our infinitesimal surface area element. And this is equal to the value of the function at the boundary. Okay, so we've got f dot dl, which is our line integral. So now what we're going to do is we're going to consider 2 points. Let's consider a point A and a point B. And let's consider that we can go from A to B by 2 paths. We can go by path 1, or we can go by path number 2. Okay, now what can we say about this, and what can we say about the line integral? Well, if we look at the tangential component of the line integral from A to B along path 1 or path 2, essentially we're going to get the same answer. Okay, so essentially what we can write is the integral from A to B of f dot dl, and this is independent of the path. Okay, what does that mean? It means it depends only on the value at the endpoints. It's position dependent. Okay, now suppose we have a closed loop. Okay, we're going from A to B and then back to A again. Well, what we previously saw is we have the integral now. Since it's position dependent, it depends only on the values at the endpoints and the values of function at the endpoints. We've got our closed integral from A to B, okay, but from A to B and then back to A. So of this path of f dot dl is going to be equal to 0. Okay, since we're going to A from A to B and then from B back to A again, this is dependent on the value of the function at the endpoints. So the integral over a closed path is going to be equal to 0. And finally, I mean, this gives us the idea then of the vector f being dependent on some scalar potential v. So finally what we can do is we can write f is equal to minus the gradient of v. And why can we write this? Well, we can write this because if we go back to what the curl of f, so it'd be the curl of grad v is going to be equal to 0. Okay. So for a curl-free field, it must satisfy. If it satisfies one, it must satisfy it all. Okay, so here's the first. This is the second one here. Our third and our fourth. Okay, so if it satisfies one, it will satisfy all of them. Okay, so now let's look at the divergence free case, and let's say that the divergence is going to be equal to 0 everywhere. Okay, the divergence of our vector field F vanishes everywhere. So now what we can write is the divergence of F, okay, is going to be equal to 0. And what we can write this as then is F means that F can be written as the curl of some vector potential A. So we look at this in just a little bit more detail and what it means. First of all, let's look at the divergence theorem of Gauss's theorem again. So the divergence theorem. And what we have with this, so we've got the integral over some volume of the divergence of F, the tau, is going to be equal to the surface integral of F dot dA. So if we look at this a bit more detailed, we can kind of break it down. What we can say now with divergence-free fields is that it depends only on the boundary line. It's independent of the surface. So we've got the integral of F dot dA. Okay, so it's independent of surface. It depends only on that boundary line. Okay, now from Gauss's law again, what we have is, from the divergence theorem, we have the integral of F dot dA, so it's the closed integral, surface integral, and this is going to be equal to 0. Okay, so what this says is that the net flux out of any closed surface is going to be equal to 0. Okay, so here we have our first point, second point, and the third point. Okay, and for the final point, it goes back to the start. What we can do is we can write the vector function F as the curl of some vector potential A. Okay, so for a divergence-free field, if it satisfies one of them, it would satisfy all of them. Okay, so it would satisfy all the conditions. So now what can we write for our vector field F? Well, to finish off, what we can write is F is going to be equal to, we just put these two theorems together. It's going to be equal to minus the gradient of our scalar potential V plus the curl of some vector potential A. Okay, I'm going to come across this as we move towards through the course over the next couple of weeks.